o'clock sharp. Okay. Again, good morning, good afternoon, good evening, depending where you are. Now, today we're going to start our the last day and the fourth day of our Waterloo International Neuroengineering and Rehabilitation Workshop. And for today's topic, we are indeed focusing on brain-computer interfacing, BMI, or brain-machine interfacing, for BCI, and brain-machine interfacing, BMI. And we have 5 speakers with us today here. And I'd like to ask Professor Guan from Nanyang Technological University of Singapore to start off today. Professor Guan, the screen is yours. Thank you.
All right, very good morning, afternoon, and evening. Thanks, Prof. Jiang, for the organizing this second workshop. In fact, 2 years ago, we met in Hong Kong, organized by Professor Wang Yuwen, which was a fantastic event. And this year, because of the COVID, so we meet online. I think it's good and bad because we can easily join. We have a large audience. So today, what I'm going to share with you is centered around the techniques which are behind the stroke rehabilitation. So the topic is about motor decoding using deep learning model, and also share some information on the interpretation part. Most of the work was done by my PhD student, Ravi. He just graduated early this year. So the background is, the outline is like this, some background information, what we are doing. And I also try to explain a few more deep learning model, which we are using for benchmarking. Some XAI technique, which has now become more popular, and how to use that to interpret, eventually could use that to improve the outcome for the stroke rehabilitation for patients. Okay, so the background is straightforward. We have seen very active research in using BCI, or brain-computer interface, for stroke rehab in the last 10 to 15 years. As of today, I think if you look at the literature, there are more than close to 50 clinical studies with different kind of sample size, which actually show effectiveness of using BCI for rehab. Of course, the principle is based on the neuroplasticity, right? Once the subject or person has, a lesion or attack by the stroke, so the motor function will have a deep, and after time, depending on the treatment and the rehabilitation, so some patients may recover faster, may come back to normal within a few weeks, or even or a few months. Some may suffer longer, and some may take a long time, but get closer to normal recovery. So depending on many factors. So in general, there are 1/3, 30% to 35% of patients who will come to this group. So that means they have to really spend a long time to go through rehabilitation, to either for occupational therapy or field therapy to recover their motor functions. So there are technologies in clinics which are useful for them to recover. Train their motor functions. For instance, robotics and so on. But we still need more alternatives for the patients to recover, especially BCI provide one of the very promising options for patients. There are 2 types of BCI, currently 2 general categories based on the principles, either BCI, motor imagery or motor intention detection, or based on neurofeedback. So these are 2 general approaches. In our study, we mostly rely on the first scenario. So is ask the person to imagine or try to attempt to move, so they can activate the neural pathway, so they can repeat the same thing. So in general, any system in BCI-related rehabilitation, it works in this way. You look at the sketch here. There's a data acquisition. Most popular, we use EEG today. Then there's a software to decode the activities. This can be used either for the motor imagery, intention-based, or used for neurofeedback. Then the feedback can be multiple way. You can use a visual. We can use can be a VR-based. You can use a optical, mechanical, or use electrical stimulation. There are multiple ways. So this is a very general setup. Most of the system people proposed or in the clinical studies fall into such general scenario. So this has been done in the last maybe 15 years, since 2005. Starting, there are groups working on this. So now they are doing a lot of clinical studies using various of scenarios. In the recent years, of course, deep learning has been really successful in other field, computer vision, speech recognition, and we also see a very big hope for BCI, which I will explain a little bit later. So in our study, mostly we use robotics, mechanical device together with the screen as a feedback. So the whole thing, the person just try to imagine or try to attempt to move the affected arms. If the person has a lesion at the left side and the right arm is affected. Most of study actually today using BCI is for upper limb. There are a couple of study on lower limb, which is probably more challenging using BCI today. But we see the trend, more and more study come to this field. So after collect the data, then the typical stage will be pre-processing, then decode. This is a traditional way of processing. But today, if you have a end-to-end deep learning, you just feed raw EEG, then you get the decoding, then you feed the results back to the subject. Okay, so this is the typical scenario we are using in our study. So this is just give you an impression. There are more than 40, close to 50 clinical studies with various size of sample subjects. So, and overall, the average improvement for BCI arm, because for some of the studies, they have a control, they have a sham group. So the BCI arm actually in average improved by around 5 point in Figure score, which is quite substantial, which has the clinical significance, not only the statistical significance, but clinically, which is meaningful. So these are a few examples in our group. We use BCI as closed loop with either available, this is Manus device, or we co-develop with our collaborators, using hand glove or purely visual feedback. So there are few studies, there are a few more, just show you a few examples. So the data later I explain, we use is basically from the study from the top 2 studies, collect data from the subjects, patients. So then the method we are going to discuss today, I mainly focus on the deep learning approach. So there are 2 very popular models which has been used or benchmarked by the BCI researchers today. One is by Lohan and etc. They propose a method called EEG-NET. Another, the group from Freiberger, Tony Ball's group, they propose a method. They have 2 architecture, one called deep convolutional, another one called shallow net. Since today I only focus on subject-specific model. We don't have a large amount of data, so we only use the shallow convolutional. So for the smaller data, the deep convolutional doesn't work as well as the shallow net. So we only use the shallow net. And also now today I also discuss a new architecture we call filter bank. C is for convolutional. So this all 3 are CNN based, but some small differences I would like to explain to you. So and also we try to compare the deep learning with the traditional feature-based field bank CSP. The FBCSP has been used quite as a lot as a benchmark to be compared, because it provide quite consistent performance, especially for subject-specific model. So we try to do a comparison to see what is the rationale behind to use deep learning, and how do those models, deep learning model, compare with the traditional feature-based model. So in summary, the feature-based model, in fact, especially for FBCSP, there are four key elements. The last one is straightforward, is classifier. So the unique part is, first is the temporal filtering. Okay, so we'll divide the data into multiple bands. Typically, you divide every 4 Hertz, which actually somehow for alpha, beta, theta, delta, theta, and alpha, they are also consistent with our neuroscience study. We normally use alpha, theta, and delta as an analysis, but beta is wider, so we divide beta into multiple bands, similar for gamma. Now, after that, the spatial filtering best is a common spatial pattern, okay, based. So it's a CSP based. So it's a spatial filter, then followed by typically we calculate the power or energy after the spatial filtering, then use this as a feature. Of course, if we have a multiple frequency band, we need to do feature selection. So reduce the dimension, normally, which should help a lot. And finally, we fit the power either in linear manner or in logarithm manner to a classifier, either LDA or SVM. So this is the typical procedure. Later, we'll analyze in terms of deep learning, what is the analogy? What is the reason behind define the CNN for EEG? We pretty much actually also have correlations with these steps. Okay, so specifically for the 3 models, I'm going to explain the 2 popular model, EEG net and this should be a shallow conv net. The deep conv net has 5 layers. For the shallow one, have 2 plus the pooling. So you see, look at the 2 structures. They are very similar. So the first layer, in fact, actually is a temporal filter, because they use 1D kernel to do a filter. Same here. So in the time domain, there's a kernel. This kernel more like an FIR filter, okay? But the coefficient is learned by the deep learning, by the whole data-driven, instead of the traditional way. So in the FBCnet, we still use the traditional filtering, use IRR, or you can use FIR, whatever filtering to really well-defined frequency component, right? You divide information into multiple frequency band. And in EEGNet and shallow net, same thing. They use the kernel. Each kernel is served as a spatial filter, temporal filter, okay, like similar to here. But of course, not exactly. So you can define multiple kernel. That means you can define multiple filters. Hopefully, the filter will capture the key information from EEG from each of the frequency band. Then the next layer, I think all the structure share the same thing called spatial filtering. Here's a spatial filtering. Here's a spatial filtering. Okay, so you can see if you look at this matrix, x-axis is time, y-axis is the channel. So you use a 1D kernel for the spatial filter. So this is analogy to the spatial filter in the FBCSP. Okay, the first part is simulate the temporal filtering. So this is quite similar. And the next stage is in the shallow net, actually is just do average pooling and come to the fluid connection. For EEGNet, there's also a summarization stage to reduce the dimension, and finally fluid connection. And here in the FBCnet, we make difference. So if you look at the EEGNet and the deep conv net, they are pretty similar, except a little bit change here. But for FBCnet, we make several changes. Beside the filtering, we don't use average pooling here. Okay, both of these structure they use average pooling, In other field, like images, sometimes people using max pooling. Either max pooling or average pooling is very popular. But if you look at EEG, actually, we try to capture energy information or power information. So we create a different layer, which we call variance layer. Just calculate variance instead of the mean or maximum max. In addition to this, we also add one more layer, multiple layer, we call high-level temporal layers, which will capture temporal information because the motor imagery or motor intention from a motor area basically is based on ERD, ERS. So there are certain temporal info which may provide additional benefit to differentiate multiple classes. Okay, so just explain to you what is the similarity and what's the difference. And bear this in mind, later we compare the performance. You'll see some interesting observations for if you compare all these three structures as well as the traditional feature-based method. Okay, so there's something interesting for us to find. Of course, there are many other approaches which are not exactly, this is also kind of similar to what we propose, but the FPCNet is more compact. Yeah, one more benefit using the filtering, actually we have much less parameters. We don't need to learn the temporal filter parameters. We just use the predefined and compare with other things. But that's a small benefit. And a few other methods also proposed to dealing with the using all based on CNN, but a different kind of presentation or different features, different input to the deep learning model. I don't go to the details. In terms of performance, they are pretty similar. Okay, say this. Then we try to first to compare the method, 3 deep learning model plus the FP-CSP using open dataset, or as well as the internal dataset from the stroke patients. So we have 4. The first one is very commonly used competition data, 9 subjects, 2 sessions, 2 days actually, from 2 days. Each session has 288 trials out of 4 classes. Okay, for each classes, about 1/4 of this number, and this is come from the 22 channel, mostly around the motor area, with the total of 4 seconds. All downsample or aligned to 250 sampling rate. Okay, 250 hertz. So 1,000 means 4 second data. So that's for competition. For that another data set from Korea University, which has a much larger population, 54, 2 classes, left and right, and imagery. There are 2 sessions. Okay, 2 sessions, 2 out of 2 days. So each day they have 200 trials, 100 for each class. And depending on the scenario, for subject dependent case means you only use the data from this subject. Typically, we use a smaller number of channels, which is 20, which give you highest performance. Of course, if you try to build a subject independent model, I'm not going to talk today, but if you want to do that, you need to look at the whole brain, all the channels, 62, which will give you much higher performance compared to 20 channels. Then we have 2 data set from our clinical study. I just mentioned the example we had. Each of the study, this is a 2 study, but the calibration follow the same protocol. So we put them together later to analyze the performance. So for the first group of patient data, we have 37 subjects. Another one have 34. Each only have 1 session. This is calibration session. Okay, the scenario is this way. We recruit patients based on the inclusion criteria, and we ask them to do the calibration. Then we to evaluate whether they are able to at least reach certain level of accuracy. Okay, if their result is very poor, they are not eligible to do the next level of rehab. Only after this, we try to recruit patients who can use BCI to reach a reasonable accuracy. typically 70% or 65%, about chance level. And each stage, for each of the calibration session, they have 160 trials for 2 classes. This is basically a detection scenario. They try to attempt to perform motor movement or intention. And we record it using a neural scan with 27 channels. Again, all 4-second length. Okay, so this is the background of the data. Just want to mention one more thing is the difference between the multi-session, a 2-day session, multi-session issue is because we know there's a variability. When you train the model on the first session or first day, different days, then you test on the second day, the performance may change. Normally it will drop. So that's kind of another factor we don't want to take into consideration to confound all the comparisons. So in other studies, we choose one of the sessions for this particular study. But if we train a model from one day to test another day, we call hold out. So here I show you the performance. So there are 2 scenarios. If we use the data from one session, we do 10-fold cross-validation, CV. So that's one performance, right? With a 1, 2, 3, 4 method with additional LSTM, but this is not always better. So I just show the results, but this is the only thing we use for the analysis for today's talk. And if we test the data, train the data on day 1 and test on day 2, this is called hold out. So this is cross session. So typically you can see there's a drop for BCI data. If let's say we use a FBCSP, the same day, okay, same session, cross validation, we can get a 75% accuracy. But if you use a cross day, the accuracy dropped to 68. Okay, similar for the career data set, used to be 64, dropped to 60. Okay, that's because of the variations between the session. Okay, now look at the shallow net and the EGNet. For the competition data, they don't perform even better than the FBCS, but close, only 2-3%. If you look at accuracy, they are not far off from the FBCSP traditional approach. The FBCnet, of course, is 2% better than the FBCSP. Okay, if you look at average, the difference sounds not so drastic. Later, I will show you the details. Then you'll see some interesting observations from the performance. Okay, not only the average performance is important, useful for us, the individual accuracy is also interesting. And for career data set, which has 54 subjects, actually deep learning perform better than the traditional approach. Okay, and the FBCnet also better than the rest. For stroke data, it's also interesting. You can observe, in fact, the performance for stroke data for stroke patients, the average performance is not too far from healthy. This is also already seen in other studies. So this is good news. Even if they have lesion in the brain, they still can perform the relatively good motor imagery to get a decent performance. Similarly, we compare to the shallow net and EGNet, not far off too much, pretty similar. And this is the FBCnet. FBCnet actually is a quite big improvement compared to the stroke patients data. Okay, so you get almost 80% in average. This is pretty high as an average performance. We all know motor imagery is very tough task. And for cross session, we can see the deep learning model typically work much better than the traditional approach. This is also a good thing. It sounds like a more robust, okay, compared to the feature-based. For at least for the competition data. For career data, it's pretty similar using a shallow net. EGNet has a better 3% improvement. FBCnet improved 6%. This is quite big. So far, this is the best result we can achieve using all the 4 data sets in 2 scenarios. Now, what is the observations of behavior of the classifier, which we can go deeper to look at the performance, compare all the 4 methods in this manner. So let me say this a bit busy picture. Let me explain to you what does it mean. So first we get all the 54 subjects accuracy. Then we sort based on FP-CSP as a baseline. We sort every subject according to their accuracy. So actually some are pretty poor, even below 50 because the cross. Then go all the way, some can reach almost 100%. So that's the distribution according to their performance, okay, based on the FP-CSP performance for each of the subjects, 54 subjects. Then we plot the accuracy of the deep learning models accordingly, okay? So the first subject has the poorest, lowest accuracy using FP-CSP. Then this three symbol, okay, either cross or this is a cross star. So these three represent three models. This is a shallow net, reduced deep net because the traditional way we call this. This blue, light blue. The orange is the EG net, and the dark blue is the FPC net. Okay, so in a first glance, you can find interesting observations from here. Although you look at average EG net and the shallow net, they are similar compared to the FP-CSP, but the behavior of individual subjects are different. So if you look at the lower part, when some of the subjects, they have a very poor performance using FP-CSP, but if you use deep learning, either shallow net or EG net, you can get a much higher improvement, right? Many of them actually improve quite a lot. However, if you look at the other side, those subjects has a very high performance accuracy using FP-CSP approach, but some of them actually drop drastically if you use deep learning. So that is one thing. So that's why in average, they are similar, but this is the things you can see. So what we hope to achieve is, for those with traditional approach, their accuracy is not good, we try to improve. But for those which are good, we try to keep. We don't want them to degrade, to become poor, right? So that is the performance for FPC net. Okay, that explained to you not only the accuracy, average accuracy is higher, but also the behavior sounds more reasonable. So if you look at the dark blue, the solid line, so at the lower part, they improve in somehow similar manner compared to the other two deep learning model. Okay, but at the higher side, they follow the FP-CSP pattern, the accuracy performance. So this is that's why we find this is probably, compare all the three deep learning models, this is more desired. Okay, there's more we hope to. And why? What's the reason? Just now I explained to you we have several differences. This change is not due to the change from the temporal filtering to temporal kernel to temporal filtering. That is a little difference. That means use deep learning end to end. It can learn pretty well the temporal filtering, okay, by itself, even if we use. But the benefit, we are using the direct filtering. There are two ways, just the two benefits. One I just mentioned, we have a less parameter to learn. That's good, especially to build a subject-specific model, you have a less data, right? Second, later we do interpretation. We can pinpoint exactly which frequency band has which corresponding to what activation model based on the XAI approach, which is another benefit. But the major improvement for this kind of pattern is due to the variance polling. Okay, just now I mentioned we don't use mean average polling, we don't use the max polling, we use variance. So we create a direct variance layer, which lead to this behavior, which sounds better compared to the other end-to-end deep learning model. And finally, the temporal high-level temporal model, temporal layers, and the last part actually push maybe 2% from the original FPC net without a high-level temporal layer to these final results. Okay, so this So look at here. In the next, actually, all the analysis we are going to use FBCnet for the analysis. And this source code also available. I hope if anybody is interested, please feel free to look at that and also to see whether there are new thinking, new ideas, new architecture you can use to further push up. Because the more we have in terms of accuracy, probably the outcome is higher, so we can expect better rehabilitation clinical outcomes from the patients. Right, so this is the deep learning. Then we look at the actual stroke data. So if we use such a deep learning model, what we can learn from the data? Okay, so from the traditional approach, unless we draw the CSP pattern, the spatial pattern, we don't have too much things we can really extract from SVM or whatever model to analyze to get insight. But here we probably have something interesting, so I will explain to you. So out of the 37 plus 34 subjects in the calibration, normally we call the screening. So everybody do one session to get an average performance, and of course based on many other criteria altogether, inclusion criteria, whether they can commit time, whether they have certain other things which prevent them from doing the actual online actual rehabilitation over the next few weeks. So finally, there are 25 patients that completed all the way from 10 to 18 weeks, 18 sessions rehabilitation. Okay, typically in 1 week, we have different scenarios. In certain scenario, the patients come to the clinic, rehabilitation center 3 days per week. Okay, some come to clinic every day. So, but altogether, we have 25 patients who complete the entire session, and we have also pre-assessment and post-assessment of the outcome using FMA. Okay, so this is the data we are using for the rest of the analysis. So just quickly, the explainable AI is one of the important areas for deep learning. In fact, actually, there are many methods being proposed, either based on mathematics or based on so-called perceptive interpretability. Okay, here you can see we try to categorize them. Then in terms of perceptive interpretability, there are also few methods based on silency, based on signal, or based on oral explanation. So most of the computational approach today, popular methods based on silency to build a heat map, to look at the picture on the left side. So why this picture is categorized as a ship? So then there's certain area of the picture which is kind of a heat map. This actually contribute more to the decision. So this is cited from the paper by Klaus Müller's group. Klaus Müller actually proposed one of the method called layer-wise relevance propagation, RRP, which is one of the first, probably the first, be applied to EEG to analyze the spatial significance and relevance. Of course, there's also other approach, so sensitivity-based and other based. So later, we use another approach called Deeplift to try to analyze which channel, which frequency band has contribution eventually to the final accuracy. And now we try to correlate those with the clinical outcomes. So quickly on the Deeplift, Deeplift actually is the decomposition approach. We try to decompose the output prediction of the deep learning on a specific input. You feed one by one, and by propagating the contribution of all the neurons in the network to every feature of the input. So eventually you can build a heat map. Okay. So in this case, actually we use the data to use the training data to build a model. Then we send every single trial to get a relevance score for each frequency and each channel. Then we average all the activation, the relevance map the scores over all the trials for each subject. So we build a subject-specific heat map score to indicate which frequency and which channel actually contribute the most to the final decision. Okay, so this is the approach. So you can refer to this paper published in ICML, which explain the mathematics how do they is calculated. So first we try to, okay, among all the 26 subjects, right? So because we have they have gone through the online, so we can estimate the average online accuracy. Okay, and also list down here. Then we try to calculate the relevance score, relevance score for each part of the brain. We divide into motor, non-motor. I mean, these two actually altogether is all the 27 channels. Then we also look at the frontal, we look at the occipital. Okay, each of the part. These are the relevance score, average relevance score of each subjects. Okay, from the calibration session only, from only the calibration. This score is not using the online data, only use the calibration data. Then we try to find the Pearson correlation between the relevance score and the accuracy. Then we can find for motor area, there's a positive correlation, which with a p-value of 0.02, which is significant. And for frontal, which is negatively correlated, which is also close to significant, 0.05. But occipital is not significant. Okay, the accuracy is not significant. So from here, you can see the motor is, the relevance score is highly correlated to this accuracy. Okay, keep in mind this here, we have accuracy, we have a relevance score. They are highly correlated. Okay, now the next step is we try to categorize the subjects, 27 subjects, into 3 categories. One category, they have a high motor accuracy. That means they have a relatively high relevance score from a motor area, right? So because they are highly correlated. So then we try to estimate the average FMA score for this group. In fact, out of 27, there are 13 of them. Okay, 25 out of 25, 13 of them has a higher motor accuracy, also the motor area relevance score. Then average FMA is 8, which is very high compared to the average. Average is 5. Another group, they have a relatively high accuracy in the frontal area. Also the frontal relevance score, the average improvement is only 2.8, which is not significant. Okay. Another group, they have a higher equal motor and frontal accuracy. Okay. In terms of the relevance score also, the average improvement is 4.5, is just on par with the average improvement. So this gives us a very good indication. So from a calibration session, we can find the relevance score which are higher, get a higher relevance score from a motor area. This patient probably get a high recovery. So you can imagine the relevance score can be served as a biomarker, as a prediction or prognosis, prognostic model for the patients before they go to the rehabilitation. So on the other hand, so from this study, which can also probably provide another, open another space, if we can find the patients, they are only, when they perform motor imagery, they use the frontal or pretty much frontal plus motor. So we teach them to learn how to do kinesthetic imagination to activate motor area. Because before they go through many weeks, we already have this information. So can we use this to guide them to perform more effective rehabilitation? These are the questions and hypotheses we are going to test in our next clinical studies. But here are the initial information give us a lot of additional things we didn't know in the past. So as a quick summary, I think my time is almost there. So deep learning, I think, is very promising for motor imagery. Not only provide good performance, but also can provide insight. This is exactly what we want. And this also new architecture, new method can come. This will evolve compared to the traditional approach, which probably much almost there. So hard to have a much improvement. And then we propose a modification of deep CNN called FBCNet, which will further improve the deep learning model or popular model. So provide additional benefit for the group of subjects. I think one of the important things we need to keep in mind, eventually we develop a system to help patients. This system hopefully will work for most of patients, not just for selective group, right? So if everybody can use it, will be more beneficial. But we all know in BCI, there are certain group of subjects, they are not able to control BCI well. So the question is, are they not able to, or are we not doing a good job to create a technology for them to do it? So if you look at a CSP, some subjects actually, if they use deep learning model, actually they can do. Why not? So this is something new for us to think further. And this also rely on the XAI, explainable AI, for us to really go back to understand what's going on. So eventually we hope to have using this technology to have a guided rehabilitation for stroke patients. With this, I close my talk. Thanks very much. We can answer some questions.
Okay. Thank you very much, Professor Guan, to have your presentation. As always, fascinating work. So we do have some questions from the audience. The first question is, why for some subjects SVM is better and for other subjects EEG-net is better? And what is the main reason that, Professor Guan, you think?
Yeah, so this is still a mystery. I don't think we have a clear understanding of this on this. Even using the XAI, we still try to figure out for individuals why the difference, the performance difference can be so big. This could be a good thing, because if we can find at least one method which can achieve certain performance, we can find the reason. If they all perform similarly, I would say it's bad news. We have nothing new to go in. So this is still an open question, but it's a very good research topic. I hope we can have in the future more people can come in to share your thoughts and ideas on this, publish more results on this.
Okay, and a follow-up: can CoVNet be used for classification when there are less number of channels?
Yeah, we did using the actually 4 channels for other tasks which perform. We also compare with the feature-based approach, which perform much better than feature-based approach as well.
Okay. So I have a question, Professor Guan. So we see that in the studies that you showed, and in many other studies, and out in there, there is a significant change in terms of the accuracy from healthy subjects translating to stroke population, whereas various reasons have been proposed. What do you think it might be? I mean, I think you probably have the one of the, if not the, but one of the most experienced researchers in using BCI for stroke population. So what are the reasons you see? Is it just because that they have this lesion in the brain, or they have limited cognitive capacity, or any other reasons that you might think?
Yeah, so from just purely from the performance accuracy perspective, actually we did the comparison with between the healthy, the matched healthy and the patients. In fact, statistically, they don't show difference. In fact, that's one of the interesting thing. That's why they're very encouraging. Of course, individual, even between the healthy subjects, also the variability is very big. Some are very good performers, some are not good. Of course, if we talk about the reasons, of course, the cognitive ability is one thing. If they can concentrate, they can perform, do something with a focus a sufficient long time, they can do well. If they tend to be very easily distracted, even fatigued, probably the performance will drop. But even these connections are not well established, I would say. So still, it's so many factors. I don't think it's so easy to say which group will be better than the other group. So far, if you look at data, we show at least the performance between the patient and the healthy subjects are pretty comparable.
Okay, that's great. Okay, in interest of time, I think there will probably be more questions coming from the audience that I will forward to you. And in interest of time, thank you again, Professor Guan, for your presentation. And
thank you very much.
Thank you. We're going to move to our next speaker, Professor Donghui Wu.
Okay, let me share my screen first.
Okay, we can see the PowerPoint slide deck.
Okay.
Yes, perfect.
Okay. Hello, everyone. This is Donghui Wu from Huadong University of Science and Technology. It's my great honor to present our recent work on transfer learning for brain-computer interfaces. This is the outline of my talk. First, I will give a brief introduction to transfer learning, and then introduce two pieces of our recent works for homogeneous transfer learning and heterogeneous transfer learning, finally conclusions and QA. First, a very brief introduction to transfer learning. The basic idea of transfer learning is to use information in source domain to facilitate learning in target domain. Let's compare that with traditional machine learning. Say here we have three subjects. For each subject, we have a two-class classification problem. Because we have a very small number of training samples, so in this case, we have only two labeled samples for each class. If we consider each subject individually and build a classifier for that subject, the generalization performance of the classifier may not be very good because we do not have enough training data. Transfer learning uses a different idea. Say now we are considering subject 1. In addition to the data from subject 1 himself, we also make use of data from subjects 2 and 3. But due to individual differences, the data from subjects 2 and 3 are not completely consistent with those from subject 1. So a simple approach to evaluate this problem is to add a smaller weight to data from subjects 2 and 3, and then combine them with data from subject 1. In this way, we have more training data for subject 1, and we can build a more reliable classifier. Then we can do this for subjects 2 and 3 in a similar way. Of course, what I just introduced is maybe one of the simplest transfer learning idea. We can develop many more sophisticated transfer learning approaches. In this talk,
excuse me, may I interrupt? I think the voice is not clear on the mic.
Yeah, I have.
Yeah.
And is the picture good?
The picture is fine, but the sound is not very clear.
The video is fine. If you have a microphone that can place closer to you, it might be better.
Yeah, thank you.
Okay, and is this better? If
I think so.
Okay, I'll have to be closer to the microphone. Okay, in this talk, we distinguish between heterogeneous transfer learning and homogeneous transfer learning. Heterogeneous transfer learning may be the most challenging transfer learning scenario. Let's use one example to illustrate that. Let's say we want to use subject 1's MI data to help classify subject 2's MI data. Here we may have 4 challenges. First, the feature spaces in the source and target domains could be different. For example, the 2 subjects could use different headsets, so we could extract different EEG features from the 2 subjects. And second, even if the feature spaces are the same, their marginal probability distributions are different. This is due to individual differences, and we cannot remove this challenge easily. The third challenge is that the label spaces in the source and the target domains could be different. For example, for subject 1, it may be 2-class classification, but for subject 2, it may be 3-class classification. The fourth challenge is that even if the label spaces are the same, the conditional probability distribution of the label could be different. Again, this is due to individual differences, and we have no easy way to remove this challenge. For homogeneous transfer learning, we simplified the challenges in heterogeneous transfer learning. For example, first, we assume that the feature spaces in the source and the target domains are the same. This can be achieved by requiring the two subjects to use the same EEG headset. But the second challenge still remains, that is, the marginal probability distribution of the features in the two domains are still different. This is due to individual differences, and this cannot be removed by designing the experiment carefully. The third challenge, we can also remove the third challenge in homogeneous transfer learning. That is, we can force the label spaces in the two domains to be the same in our experimental design. But the fourth challenge still remains. That is, the conditional probability distribution of the labels are different. And this is again due to individual differences. Next, I'm going to introduce Euclidean alignment, a recently proposed approach for homogeneous transfer learning. It is a very simple approach with only two steps. Assume here we consider each subject individually, no matter whether it is a source subject or a target subject. Assume a subject has n trials. We first compute the arithmetic mean of all covariance metrics of all the trials. In this step, we compute R bar, which is here. And in the second step, we perform alignment by left multiplying the original EEG trial matrix Xi by R bar to the power of -0.5. In this way, we align the EEG trial, which is denoted as X tilde I, and then in all subsequent signal processing and classification, we use X tilde I to replace the original Xi. That's it. It's a very simple pre-processing step. After Euclidean alignment, the mean covariance matrix of all aligned EEG trials becomes the identity matrix, and hence the distributions of the covariance matrix from different subjects are more similar, and this will facilitate later signal processing and machine learning. Here we compare our proposed Euclidean alignment approach with a remaining alignment approach proposed earlier in the literature. First, we compare their reference matrices. In RA, they compute the remaining mean of resting state covariance matrices. But in our EA, we compute the Euclidean mean of all covariance matrices. Here, EA has two benefits. First, it can be computed much faster because the Euclidean mean has a closed form solution, but the remaining mean does not. It's very time consuming to compute the remaining mean. And the second benefit is that EA does not need any label information, but in remaining alignment, we first need to identify the resting state, which needs label information. After alignment, for alignment, RA aligns the covariance matrices in the remaining space, whereas our proposed EA aligns the raw EEG trials in the Euclidean space. The benefit of EA is that because everything is in the Euclidean space, any Euclidean space algorithms, such as the signal processing and machine learning, can be used later, can be applied to the aligned EEG trials. Whereas for RA, all subsequent algorithms need to work in the remaining space, but we have a very small number of such algorithms. So EA is much more flexible than RA. And both approaches have the benefit that distribution from different subjects become more consistent after alignment. Next, we performed experiments to verify the effectiveness of EA. We used the 2 multi-imagery datasets and 1 ERP dataset. Actually, I think the one of the datasets was also used in Featurebased talk. Before actual classification, we used the TSNE to visualize the effect of EA. Let's focus on the first row. Here, we use subject 1 as the target subject and subjects 2 to 9 as the source subjects. In the first figure, each blue dot represents an EEG trail from a source subject, and each red dot represents an EEG trail from the target subject. We have many more blue dots than the red dots because we have 8 source subjects, but only 1 target subject. We can observe that the distribution of the blue dots and red dots are quite different. For example, in this area, we have plenty of blue dots, but no red dots. If we combine data from source domains and the target domain directly, because their distribution are so different, we may not achieve good performance. But after EA, we can observe that the red dots and blue dots are more consistent. This would facilitate later signal processing and machine learning. When subject 2 is the target subject, we can have the same observation. Next, for the actual classification performance, first we consider the offline multi-imagery classification. We compare the baseline approach is the CSP LTA, which combines the data from source and target subjects directly, and then performs CSP and LTA for classification. Our approach is to apply EA first to align the EEG trails from different subjects, and then perform CSP and LTA. We can see that by adding this very simple EA pre-processing step, we can dramatically increase the classification accuracy, especially on the first data set. We can increase the accuracy by 20%, and for the second one, also about 6%. We also compared our approach with RAMDRM, an approach proposed in the literature, which used the remaining alignment followed by a remaining space classifier. We can observe that our approach also performs that remaining alignment approach. So this is for classification. For classification accuracy. Next, we also compared the computational cost of different approaches. Here we can see that the EA approach can be performed much faster than the remaining alignment approach. These are the results on the multi-imagery datasets for offline classification. We also applied the approach to the ERP dataset and observed similar results. By adding EA to the baseline approaches, we can almost always improve the performance. For online classification, we have similar observations. In summary, here, the question we are considering is how to cope with individual differences so that better learning performance can be obtained for a new subject with the minimum or even no subject-specific data. Our approach is to use Euclidean alignment to align EEG trails from different subjects in the Euclidean space to make them more similar and hence to improve the learning performance for a new subject. Our proposed EA has 3 desirable properties. First, it works in the Euclidean space, so we have a lot of freedom to choose the subsequent signal processing, feature extraction, and machine learning approaches. And second, the computational cost is very low. And third, it is completely unsupervised. So we do not need any label information from the new subject. In summary, EA is very effective, efficient, and easy to implement. And it can greatly facilitate the transfer learning in PCIs. And we think that EA could be an essential pre-processing step for EEG-based PCIs. For the next part, I'm going to briefly introduce another proposed approach, label alignment for heterogeneous transfer learning. We already introduced this page before. In heterogeneous transfer learning, we need to consider all these 4 challenges simultaneously. That is, the feature spaces of the 2 domains are different, and their marginal probability distribution are different, and the label spaces of the 2 domains are different, and also their conditional probability distribution are different. So this is a very challenging scenario. In this paper, we propose the label alignment for different set domain adaptation. Different set domain adaptation is illustrated here. It means that we have 2 domains, source domain and target domain, but the classes in the source domain may be completely different from those in the target domain. For example, in this figure, for the source domain, we have classes A, B, C, D, but in the target domain, we have classes E, F, G, H. They could be completely different. So this is a very challenging transfer learning scenario, but still, by carefully designed algorithm, we can still perform transfer learning here. The label alignment approach is essentially an extension of the previously proposed Euclidean alignment approach to heterogeneous label spaces. The main idea is to independently move the per-class coherence metrics of each source subject to center them at the corresponding class center of the target subject. And that is, for Euclidean alignment, we try to align the overall distribution of data from each subject. But here, in label alignment, we consider each class separately, and then we, for each class, we try to align the data from the 2 domains. And this is the general idea. But from this idea, we can see that in label alignment, we need to know some label information in the target domain. And otherwise, we cannot perform a per-class alignment. If we have multiple source subjects, we can perform label alignment for each source subject separately, and then use ensemble learning to aggregate the final results. After label alignment, the source and the target domains have the same label set, and the trials in the same class are aligned. Then trials from the 2 domains can be combined directly for feature extraction and classification. Or we can use additional transfer learning approaches after LA to further improve the performance. Next, I'm going to briefly introduce the label alignment procedure. We assume that this is an M-class classification problem, and the source and the target subjects have the same number of classes, but their class labels are partially or completely different. For example, for model imagery, the source subject may imagine the movement of the left and the right hand, but the target subject may imagine the movement of tongue and both feet. So their class labels are completely different. The goal here is to use the source data to help the classification of the target trials. And again, it has only 2 steps. The first step is to compute a transformation matrix AM for the trials of the M's class from the source subject, so that the distance between the mean coherence metrics of the corresponding classes in different domains are minimized. This transformation matrix AM is solved from this equation, and it has a closed form solution, also computed from the coherence matrices. But here, these coherence matrices are per class coherence matrices. Once we have AM, we can transform each trial AJ of the source subject to a new trial by left multiplying the original trial by AM. So this procedure is very similar to those in EA, except that here we perform per class alignment, but there we perform per subject alignment. One challenge here is how to match the label from the source and the target domains, because they may have different labels. When the source and the target label sets partially overlap, for labels in common, we just match each source label with the same target label, and then randomly match each remaining source label with a remaining target label. For example, if the source domain label set is ABC and the target label set is ADE, then we match source label A with target label A because they are in common. And then we can match source label B with target label D and source label C with target label E. Of course, we can also switch D and E. It does not matter. At least our experiments show that. If the source and the target label sets are completely different, we can randomly match the source and the target labels. The results, we can achieve similar results. This is a direct comparison between Euclidean alignment and label alignment. So for Euclidean alignment, we, okay, 5 minutes. For Euclidean alignment, we align the overall distributions of the data from each subject. But for label alignment, we align data from the same class but different domains, so that data from different classes, data from the same classes are gathered together, but data from different classes may become more separated. This may be better for later classification. So these are the major differences between EA and LA. But as mentioned before, label alignment needs some label information from the target domain. We also performed experiments to verify the effectiveness of label alignment. Here we used the two multi-imager data sets used before in the EA experiment. First, again, we used the TSNE to visualize the effect of LA. In the first row, we select the subject 1 as the target subject, and then use the subject 2 to 9 as the source subjects. Here, different color means different classes. So, and the blue dots are data from 2 classes in the source domains, and the black and purple dots are data from the 2 classes in the target domain. We can see that before alignment, the data from source and target domains almost completely separated. So we cannot simply combine this data and then perform classification. After Euclidean alignment, the overall distribution become more consistent, but different classes are mixed together. But after label alignment, the different classes are clearly separated. So we can expect better classification performance. In our experiments, we considered 3 scenarios and 2 questions. The first scenario is that the 2 domains have the same feature space and partially overlapping label spaces. The second is the 2 subjects have the same feature space but completely different label spaces. The third is that the 2 subjects have different feature spaces and also different label spaces. This is the most challenging transfer learning scenario. For each scenario, we also try to answer 2 questions. The first is, can LA be used as an effective pre-processing step before feature extraction and classification? And the second, can it be integrated with other transfer learning approach to further improve the classification performance? Of course, the answers to all these questions are yes, as verified by our experimental results. But due to time limit, I'm not going to introduce the details of these results. But anyway, this shows that LE can improve the classification performance. So in summary, here we proposed label alignment to handle the most challenging heterogeneous transfer learning scenario, which considered simultaneously cross-subject, cross-headset, and cross-task transfer. And that is the source and the target domain subjects. They use different EEG headsets. They could perform different motor imagery tasks, but still we can use label alignment to perform transfer learning to improve the learning performance for the target subject. For final conclusion, we introduced the two transfer learning approaches: Euclidean alignment for homogeneous transfer learning and label alignment for heterogeneous transfer learning. They all demonstrate the outstanding performance, and both of them can be used as pre-processing steps in transfer learning settings. They are very easy to implement. And here are the references, and we also have the source code online on GitHub. So please feel free to use them. And if you find any questions, please do let us know so that we can improve them. All these works are done by my students, and thank you. That's all for my presentation. I welcome your questions.
Thank you very much, Professor Wu, for your nice and very interesting talk. And I see that there will be questions coming from the audience. So the first question, so I guess first question actually is already asked earlier. Would the speakers be able to provide their slide deck for our audiences? Of course, this question for you, but for others.
Yeah, at least for me, yes.
Okay, thank you. So I do have a question, or rather a comment for you, Professor Wu. So the alignment, the transfer from different subjects between a group of subjects and a new subject, of course, it's always a nice feature to have. But when what kind of application scenario that you believe the ability to transfer from one user to another user will be very beneficial? I mean, I can imagine that if, when we, for example, in a patient who uses BCI, once it's calibrated, you need to calibrate anyways, right? So
yeah.
Calibrate it for that particular, say, a stroke patient, right? So in what kind of scenario that you believe this type of transfer learning will be a very powerful and very desirable feature?
Yeah, as you just mentioned, I consider the scenario of calibration. No matter whether the new subject is a healthy subject or a stroke patient, we need to reduce the calibration time, and especially for some patients, maybe he can easily get fatigued, so we need to reduce the calibration time as much as possible, and I think the transfer learning could be a very good option.
Okay. Yes, that's right. That's because for a stroke patient, the window is very short, right? So you don't want to spend half an hour just to calibrate the system. You want the system to be able to use immediately as fast as possible. That's correct. That's correct. Okay. Thank you. And I think we may have other questions coming, and please monitor the Q&A area. And I will also sort of forward the questions to you when it comes.
Okay, yeah. I can answer the questions using text.
Okay, thank you very much again, Professor Wu. And we will move to our next talk by Professor Meng. And
okay, thank you, Professor Jiang.
The team will continue with two talks. So, Professor Meng.
Hello. Yeah, I will share my screen right now.
Please share your screen now. Yeah.
Okay, looks good.
Yes.
Okay, thank you.
So the screen is yours.
Okay, hello everyone. Good morning, afternoon, and evening. And today I will present a topic of exploring fatigue induced by motor imagery-based brain-computer interface control. And this work is done in Shanghai Jiao Tong University. And my talk includes 4 parts. First, I will give a brief introduction about my research background of the fatigue and the brain-computer interface. Then I will present the experimental design of inducing fatigue in a motor imagery-based BSI control. And in the third part, there will be the data analysis and the results for the behavior and the electrophysiological data. And the part 4 will show the conclusion of our study. So various previous researches show that when a cognitive task is repeated over a long time, considerable mental effort is required. Thus, the error rates might increase, and the subject could even report a sense of mental fatigue. So for example, Leonard and Treadle and his colleague designed an experiment of solving mathematical problems, and they asked their participants to solve the math problem as soon as possible until they quit from exhaustion or until 3 hours has passed. So after analyzing the behavior data, they found the subject's response time has increased across the task period, and they didn't find any error rate change significantly. On the other hand, and the grand average of EEG, power spectral, and also the topography maps of the peak frequencies in both the theta band and alpha band showed a consistent increasing trend across the different, like the early, middle, and late period of their study. And here the theta means the 4 to 8 hertz, and the alpha means the 8 to the 13 hertz frequency band. So similarly, in another study, Lin Yao and his colleague showed a study that the 2 monkeys performed a vigilance task. So they asked the monkey to touch a switch within a proper time after the go cue appears. So in order to get a reduced reward. So the reaction times of correctly performed trials are plotted in this figure B here as black dots. And the smoothing green line is the estimation of task performance. So as you could observe, the number of correctly performed trials decrease across the task period, since the whole task lasts almost about 2 hours for the animals. And also the average power spectral of a particular ECOG electrode at the FZ is shown in this figure. And roughly from this figure, you can see the power from the theta and alpha band increase whenever the error rates increase or whenever their accuracy decrease. So the further analysis about all of those ECOG electrodes across the whole brain shows that the correct and incorrect, so the correct trials is presented as the blue lines here, the power spectral for the correct trials, and the power spectral for the incorrect trials is represented as the red lines. And you can see the power spectrum of the correct and the incorrect response trials in each ECOG electrode in this figure. And clearly we could see that the higher spectral power of theta and alpha band for the incorrect trials. So this may indicate that the performance decrease as the task is performed repeatedly over a long time, and mental fatigue might be induced across the time, especially at the end of the experiment. And the global increase of the theta and the alpha band power across the whole brain might be an indicator of the mental fatigue. So next, I'll give a brief introduction about the Brinkley interface. So since BCI is a novel technology which can directly decode a person's intention from hers or his neural signals, so motor imagery-based BCI and steady-state visual evoked potential-based BCI were two commonly used non-invasive BCI paradigms. This has also been mentioned in today's workshop. So both modalities provide a certain information transfer rates, but in the prolonged operation, the fatigue might arise. So how does the fatigue might affect the performance of BCI is worth investigating. So previously, Charlton and his colleagues evaluated the fatigue in the SSVP-based BCI. And in their study, they found increasing in alpha band power and also the theta over the alpha band power. This index are also associated with the increasing of the fatigue level. In this study, they found that the amplitude and also the SNR of the elicited SSVP response. So here they performed a single LED flash at the 15 Hertz. So this blue line represent the SSVP amplitude response at the later stage of the task, and this red line represents the response at the beginning of this task. So their conclusion is that fatigue might have negative effects on the SSVP-based BCI performance. That is because the elicited SSVP might be reduced due to users' fatigue, as this blue line is smaller than this red line. So, however, in this study, the authors didn't mention whether the online SSVP-based BCI is performed, and maybe no feedback is provided to the subject. So, based on the previous research literature, our research objective is to investigate the fatigue effects on the motor imagery-based online BCI. So first, I will introduce our experimental design of inducing a fatigue, prolonged motor imagery BCI control. So here in our study, we used left versus right mental imagination to perform the 1D cursor control. So each subject was required to finish 4 sessions of the experiment, including 1 training session and 3 experimental sessions with various resting ways. So in the training session, the subject were instructed to be familiarized with the BCI environment and how to do the motor imagery-based BCI task. And after that, each subject finished another 3 experimental sessions in different days, and the resting approach was arranged in a pseudo-random order. So that means 3 different resting conditions are designed as follows. So in the no rest condition, so in each experiment, we have 400 trials. In total, the experiment lasts for about 2 hours. So in the no rest condition, in the last 200 trials were immediately followed after the first 200 trials. That means there is no a rest between them. But in the other 2 resting conditions, they have a period about 16 minutes, either eyes open or eyes closed resting period. And also at the beginning, as well as at the end of the experiment, a multidimensional fatigue inventory and also a short stress state questionnaire were also used to measure subjects' fatigue level in our study. So this figure shows the experimental design of a single trial structure. So we will ask the participant to perform motor imagination in order to generate the proper control signals. Then the EEG signals from their scalp were continuously acquired, computed, and translated into command signals to control the movement of a pink dot cursor. Since the subject received the online feedback, we applied an online adaptive classifier to compensate the non-stationary of EEG features. This online feedback and the adaptive classifier might affect the negative effect of fatigue to BSI performance in maybe a complex way. Thus, later, we will try to analyze the change of two commonly used features to separate out the effects of an adaptive classifier. So this slide shows the pipelines of our data analysis. So artifacts were first corrected with the artifact subspace reconstruction approach, and then the signal were bandpass filtered into 0.5 to 45 Hertz, and then the data were downsampled to 200 Hertz. And after that, the independent component analysis was performed on the data of each session to further remove the artifact. So we will analyze the results of the questionnaire and also the BSI behavior performance, including the percent value correct and also the information transfer rate. And lastly, we also will contrast the change of power spectral prior to and post the resting period, and also ERD, ERS, and ERP comparisons between prior to and post the resting periods to be analyzed as well. So next, I will present the data analysis results. So the first row shows the group average difference of the SSQ, the stress questionnaire scores between prior to and post resting period in this figure, in this left upper figure. So the average score of this engagement decreased in all three sessions, but the statistical analysis revealed that the difference was significant in the no rest session. And there was also a significant increase of the distress in the eyes open rest session. So for the multidimensional fatigue inventory, the average score of general fatigue increased in all three sessions. There were significant variations in these eyes open and eyes closed rest sessions. And for the mental fatigue, it also increased in all three sessions. And also there was significant variation in the eyes open rest and eyes closed rest. So here shows the average. This like lower left panel shows the average BSI performance of all subjects across the three sessions. And also in this subfigures B, we can see the percent value correct and the PVC accuracy and the ITR of each session prior to and post the resting period. We didn't find any like significant change. And also we analyzed the different band power change in the first 100 trials, and the results was shown in this figure. So it shows the contrast between the first 50 trials versus the 51 to 100 trials. So we didn't find any like significant change in the theta band power but we find like the alpha band power in channels located over the sensory motor area has significantly increased, and on the contrary, the baseband power over the frontal area increased most, and also increased in the sensory motor area. This was roughly consistent with the previous results. So the alpha band power increase. And we also analyze the alpha band power variation for each session for the no rest, eyes open, and eyes closed sessions. So the first row shows the alpha power of most channels increased in all sessions, regardless of the rest type. And the second row of the topography shows the difference of the variation between two different sessions. So we contrast, for example, the eyes open to the no rest session. And we find that the effect of eyes closed rest was significantly different from the other two sessions, which means this is the right target trials. So this result means that in the right target task, the eyes closed rest might have an inhibitory effect against the increase of the 8 to 13 Hz alpha band power as the parietal and occipital area. That means the resting using the eyes closed condition might have this inhibitory effect against the alpha power increase. This is the similar analysis for the left task trials. And we also find the alpha band power variations for this left targeted task. And this, for the first row, the results is similar to the right hand target task. And the second row of this figure shows the variation difference between sessions. That means also contrast the different sessions in the alpha band. And from the second row, we can see that the effect of the rest was statistically different between the no rest is statistically different between the other two sessions for the left target task, and also as the parietal occipital area, both the eyes open and eyes closed resting with has inhibitory effect against the increased tendency of alpha power. However, it looks like the eyes closed rest had a stronger effect than the eyes open effect. And also we analyze the average ERP amplitude during the 300 plus minus 50 millisecond period after the target appeared. And this was given in the first row. And we also analyze the average ERP response after the cursor appeared. So the ERP response for the cursors showed in the second row. So the ERP amplitude mainly maximized in the occipital area, and also it showed a lateralization in most conditions. And this is consistent with our experience. And also from the topography, it also a slight decreasing trend of ERP amplitude could be observed either for the right target and the left target. So based on the decreasing trend observation, we investigated we statistically compared the ERP amplitude between prior to and post the resting state period. So the average ERP amplitude for the later 200 trials was weaker than the first 200 trial. And for the right target, for this right target, the analysis of ERP amplitude, especially in the contralateral PO3, indicated that the ERP caused by the target appeared significantly decreased especially in the no rest condition. However, for the left target, the analysis of this ERP amplitude in the contralateral P04 didn't show significance in the no rest. Instead, it shows significant difference in the eyes open sessions. But in the when the cursor appears in this similar site of P03, we found a significant decrease of the ERP amplitude in the no rest session compared to the eyes closed resting approach. Okay, and we also analyzed the ERD and ERS of C3 and C4 in the first 200 trials for all the sessions before any resting period happens. So the absolute amplitude of ERD for both C3 and C4 were stronger in the first 100 trials, as you can see from the blue curve and the red curve. Also, C3 had a greater ERD than C4, and this is reasonable during a right-hand motorimetry task. Also, the topography map of variation and statistical analysis results are shown in this figure B. It also proves that compared with the first 100 trials, ERD of the later 100 trials, that means from 101 to 200 trials, the ERD decreased on both sides for the task of right-hand target. However, in the control task of the left target, we didn't find any ERD significant change. So we also found an interesting phenomenon during the resting period. So this slide shows the data in the 16 minutes resting period. So during the resting period, the subject basically didn't do anything except totally relax. So the band power change of the theta, alpha, and beta were analyzed separately, and the contrast of power change between two different periods were shown in this topographies separately. First, in this theta band power analysis or analyzed in the first row in subfigure A, and the theta band power had significantly increased during the eyes closed rest, but the theta band power remained basically unchanged during the eyes open rest. So the alpha power under eyes open rest kept no significant change across the session, but the change of alpha band power displayed a different tendency under the eyes closed condition. So during the eyes closed rest, increasing tendency was found in the first 110 seconds, while the last 850 seconds had a decreasing trend for this alpha band power. So, and also we found statistical significance for this analysis. And previously we mentioned that the adaptive classifier might have some might affect the fatigue effects, since we will adapt our coefficient of classifier all the time. So the fatigue might be canceled due to the adaptive classifier. So we analyze the change of the Fisher score and the mutual information change with respect to the band power features of the last 200 trials versus the first 200 trials. But this offline analysis, we didn't see any significant change of features separability due to this prolonged BSI operation. that this offline analysis, in a certain sense, might suggest fatigue might not induce or might not significantly affect the BSI performance in our study. So the last, I will give some conclusions. So first, we show that the prolonged multimemory BSI operation might have effects on the electrophysiological indicators and mental state, but its effect on the BSI performance is not significant, at least in our study. Second, the alpha band power in the sensory motor area has an increasing trend, but the ERG modulation level seems to decrease, and the ERP was found asymmetric and seems to decrease as well over time. And in the eyes closed rest, it caused the alpha band power increased and a subsequent decrease during the resting period. And it seems it has a stronger effect than the eyes open rest on the inhibiting the increasing trend of alpha band power in the parietal occipital area. So that's closed. That's all of my talk today, and I'm happy to get any questions from you. Thank you.
So far, I think that some questions will come in. Professor Mom, so how do you think the potential effect of fatigue or the lack of effect of fatigue, the influence on BCI performance can translate to applications such as applications?
Yeah, I'm sorry, I didn't take the last part of your question. How to translate to,
for example, the applications in rehabilitation or neurorehabilitation, such as, for example, stroke or spinal cord injury. In these kind of population, do you think the fatigue or the fatigue?
Yeah, I think that's a very good question. Yeah, that's a very good question. But due to the network problem, I didn't hear your last sentence very clearly. But I roughly get what you said and your meaning. I think compared with since our study is done in the population of the healthy subject, and so in the healthy subject, usually probably. Especially most of our subjects are young college students, so they might not easily get fatigue. But for the patients, there is some. I think there is a literature show that they might get fatigue easier than the healthy population. I think at least in your study, we didn't find. We did find maybe fatigue was indeed induced, since we did find the consistent electrophysiological change. This change is consistent with previous literatures, but we didn't find any BSI performance change in our study. So partially it might be because the method or the method we use, it might not so sensitive to the fatigue. I think that might be one reason. And if that is the case, I think that might be worth to try whether it's also held in the maybe the patient population. If that is held, I think that's might be a good side for the clinical application, I think.
Okay, yeah, thank you. I have a question from the audience. Thank you, Professor Mon. Is the effect of fatigue on upper limb MI, BCI, to motor imagery BCI influenced by the use of dominant versus non-dominant hand per subject?
I think that's an interesting question. And since in our study, we most of the subjects are their dominant hand are right hand, and I think that's a common common problem in the BCI, since it's hard to find a lot of those left-handed subjects. So I cannot say any conclusive things.
So in your analysis, do you have the demographic of right versus left hand when you recruiting participants? Like,
Yeah.
Take.
So
do you see any? Do you see any anecdotal evidence of the effect of hand dominance?
Yeah, from my personal experience, I did find I didn't have some experience. I feel like the left-handed subject might be have some advantage to perform the BCI, but that's only my personal experience. And it seems there is also some publication about this dominant hand versus non-dominant hand. It looks, if I recall correctly, they did find some a significant difference. But in my study, I didn't do that since we cannot recruit a lot of left-handed subject. Yeah.
Okay. So actually, there's lots of questions. So another one, I think it's interesting.
Thank you.
About SSVEP, do you investigate the difference between visual fatigue and think it's more effective or effective on the performance?
I'm sorry, due to the network, I didn't hear clearly.
Due to visual fatigue and eye fatigue, I think there's a difference.
Okay.
So which type do you think it's more problematic?
I'm not sure about that. Since we didn't do SSVP task, in my introduction, I introduced one previous publications. They have done the SSVP based experiment, and in their results, looks like they found even they only do maybe half an hour experiment, they found some significant change of those SSVP response. The amplitude, they found the amplitude decrease. So I'm not sure whether it looks like that is from the visual fatigue.
Okay. Okay, so actually there's still two questions, but I will forward that to you on the Q&A area. Maybe you can see them as well. In the interest of time, we'll take a quick 5 minutes break, and then we'll come back for our next two talks by Professor Dario Farina and Professor Emmy Osborne. Okay, so we'll come back at 10, I would say 53, 54. Okay, let's take a 5 minutes quick break. Okay, thank you again, Professor Mon.
Thank you. Thank you for letting me.
Okay. I think we can start our next talk now. Okay, so welcome back, everyone. Let me start our second half of today's session with a talk from Professor Dario Farina. And Dario, I think you can share your screen now.
Yep, will do. Yep.
Yeah, the screen is yours, Dario.
All right. Hello, everybody. Thank you, Ning. Yeah, my talk today is related to non-invasive brain-computer interfaces, and specifically, I will discuss the uses of BCIs to induce plasticity in the nervous system. And in this first slide, you can see actually the cover of a very recent special issue of the Journal of Physiology, entirely dedicated to BCI and plasticity, from which I've taken some of the materials I am presenting, and specifically a review paper where a taxonomy of brain-computer interfacing to induce plasticity has been provided. So I will discuss some of this material in my talk. So as we know and as we have heard extensively today and in the previous days, BCIs can be used in a variety of different ways to control external devices, such as wheelchairs, or to communicate. However, BCIs are also inducing, every BCI basically induces plasticity, so they have a neuromodulation effect. And this is because BCIs are closed loop systems. So in addition to extracting and decoding brain activity, the brain receives a feedback in various ways. So this could be a visual feedback, could be haptic feedback, could be other type of feedback. And in doing that, the brain adapts to the machine learning algorithms or to the specific implemented BCI. So recently, as I mentioned, we tried to discuss a taxonomy, a classification of brain-computer interfacing, non-invasive specifically in relation to the ability to induce plastic changes, or better, we try to classify approaches of brain-computer interfaces designed to induce plasticity in specific ways. So in this the horizontal classification of this grid, you can see operant conditioning and classical conditioning, which are two different ways of operation of BCI paradigms. So operant conditioning is when the subject is in the loop and the subject actively change brain activity as a consequence of a reward or a visual or other type of feedback. Classical conditioning is when the subject is not operating and modulating the brain activity, but rather generating brain activity, which is then associated to feedback that could be stimulation of the peripheral of the central nervous system. In the vertical classification of this grid, you can also see BCI paradigms that are based on motor processing, meaning BCI paradigms where the cortical activity is modulated in association to movement, to imagined movement, or not related to motor process. So in idle state. So this is a classification that probably is not that strict. There could be approaches that are in between these classes, but it helps in defining the neurophysiological mechanism that underline the induction of plasticity by BCIs. Within this scheme, every specific BCI has a heuristic. So every BCI within this scheme will depend on the features of the EEG, on the type of feedback, and so on. Here you can see a number. Actually, I collected just some representative cases of BCIs designed to induce plasticity and specifically designed for therapeutic purposes. So also a number of common characteristics. In this case, for example, you have a BCI system in which EEG activity is decoded in order to induce functional electrical stimulation, in this case for grasping. And in this other case, just to cite two examples, we have a similar system in which EEG activity is controlling an active orthosis that provides feedback to the subject by passively moving the end. So many of these approaches are based on the concept of associativity. They are associative BCI somehow. in many of these approaches, the underlying of associating motor commands with afferent feedback or motor commands with stimulation of central or peripheral nervous system. And we have actually a large literature on more basic neurophysiological studies, not necessarily from the BCI literature, that tells us some of the mechanism of induction of plasticity when we associate various types of stimulations with motor commands, and eventually with afferent feedback. So, for example, we know that brain stimulation associated to movement induces cortical plasticity. This is a recent study by Ibanez studying a paradigm in which you stimulate the brain shortly before an action, a voluntary action. And also the stimulation is done in different ways to look at different brain circuits, posterior anterior or anterior posterior stimulation. And this study tells us, so this is sort of an associative study where we associate brain stimulation with volitional command. It's telling us that the specific brain circuits involved can be diverse, and we have to target the right brain circuits in order to associate plasticity. For example, here we have the imitating cortical excitability. In the case of posterior anterior intervention and assessment, indicating an increase in cortical excitability, which is not observed when we look at different circuits with another type of stimulation. So this is not a BCI study, it's a study from the basic neuroscience field, telling us something about the specificity of the circuits involved, and also telling us something about the importance of timing in the association, in this case, of brain stimulation with volitional motor command. Another classic paradigm that is often investigated in basic neurophysiological assessments is pair associative stimulation. This is another associative paradigm which is particularly relevant, as we will see when we discuss BCI research. So pair associative stimulation is based on a relatively simple concept. It is a pair of stimuli, from which the name, and the first stimulus is a peripheral stimulus in a peripheral nerve, and this is followed with a certain interval by a stimulation of the motor cortex. And this pair of stimuli is repeated multiple times, and if this is repeated a sufficient number of times, we observe an increase in cortical excitability following the intervention. Now, the critical aspect here is that the increase in cortical excitability strongly depends on the stimulus interval in the intervention. And specifically, there is a rather small range of values that indeed provoke an increase in excitability. So again, the concept here is that timing is crucial, and so associative paradigms of this type are related to so-called associative plasticity. When we have two events that have to be synchronized in time with a very specific delay in order to promote a plastic effect. So given this basic neurophysiological knowledge, some years ago, now around 10 years ago, we started a series of studies, and Ning was very much involved in these studies together with me and Professor Mark Kersting, in which we tried to look at the mechanism of associative plasticity when we operate brain-computer interfaces in order to have a better translation of brain-computer interfaces for therapeutic interventions. And we started with experiments that were mimicking the classic pair stimulation experiments that I have shown you before. Specifically, we had experiments in which we recorded EEG, so this is the BCI part, and then we stimulated the peroneal nerve, and the stimulation was triggered by specific characteristic of the brain waves that we detected. And we were particularly interested in so-called movement-related cortical potentials that are slow potentials, slow negative deflections that are preceding a movement and then a rebound following the movement. So the peak negativity indicates the time approximately where the motor cortex is releasing the command to the spinal cord and therefore eventually to the muscles. So we were looking at a setup of this type, and we wanted to understand how crucial is the association between motor command and this peripheral stimulus. So the idea is that this is a paradigm of associative plasticity, meaning that a motor command is associated to an afferent volley. And in order to prove that this is following the basic mechanism of associative plasticity, we had to investigate the timing and how important is the timing. So the idea is very similar to the pair stimulation, but in this case, it's in a BCI paradigm. So we have a brain activity, and we trigger with this brain activity a peripheral stimulation. And then we repeat this intervention a number of times. And before and after, we test the excitability of the motor cortex by motor evoked potential. And so the pre and post motor evoked potential will inform us on potential changes in the excitability of the cortex induced by the intervention. So we put together, this is around 10 years ago, in my opinion, an interesting study in which we looked specifically at the timing. And so given the slow negative potential recorded by EEG, we had a stimulation that occurred either a bit before the peak negativity or around the peak negativity or a bit after the peak negativity. In time in between the stimuli is just a few hundred milliseconds. So basically, we have one session in which we have the association between cortical activity and stimulus with this timing in between, and then another session, another day with this timing, and a third session with this time. If we look at a single case result, this is the MEP indicating cortical excitability before and after the intervention. And this is in the case where the stimulation is before the peak negativity. This is the case in which the stimulation is at the peak negativity. And this is the case when the stimulation is after the peak negativity. And now in this single case, I will show you the statistics in a moment. You can see that we have a clear increase in cortical excitability as evidenced by the motor evoked potential only in one of these sessions, which is when we stimulated the peak negativity. And from the neurophysiological point of view, this made a lot of sense because the stimulation around this point implies that the afferent volley would arrive at the brain somehow in a delay that is consistent with what the brain would expect after releasing a motor command. There is a release of a motor command, and then there is an afferent volley arriving with a delay which is within what is expected in a sensory motor loop. And on the contrary, the other two sessions, in this case, the afferent volley would arrive much later with respect to the release of the motor command, and here it would arrive when the movement is still prepared, and so much earlier. So this result makes sense, and if we look now at these results a bit more in detail, so in this case we have a stimulus response curve, so we have the amplitude, the MEP, when we check the TMS intensity before and after the intervention. And here you have the stimulus response curves before and after an intervention when the stimulation is before the peak negativity. In this case, we have afferent volley when the movement is prepared and we don't have any change. And now in the other section, in which we have the stimulation at the peak negativity, we have a clear increase in excitability, and when we are too late, we have no change. So these results were amazingly consistent. They were very, very clear, and they were substantially different from one session to the other. So just a few hundred milliseconds difference in this timing were causing a completely different effect. It told us that the mechanism we were looking at indeed is a classic mechanism of associative plasticity or ambient plasticity at the system level, and that it could actually be used as a way, as a very efficient way to induce plasticity in a BCI paradigm, in particular to increase excitability. We also had a number of control conditions. I will not go into details. This is in a paper published some time ago, in which you have, this is the condition that I've described, increase in the MEP, in the motor evoked potential, when we have the exact timing. And there are a number of control conditions that tells us that the increase in excitability is indeed due to the pairing of the motor command decoded with the BCI and afferent volley, and not, for example, to the fact that the subject was imagining the movement many times or was attentive to the movement or simply because of electrical stimulation. These are all control conditions. So then we went on by looking at the same paradigm and now asking ourselves if we could induce similar changes in cortical excitability with a different way to induce an afferent feedback. So instead of providing a single electrical stimulation pulse, we had experiments looking at triggering the movement of the foot through a motorized ankle-foot orthosis that you can see here. So the concept is the same now. So we have an exact time in between the peak negativity of the MRCP, the movement-related cortical potential, and we compared electrical stimulation with respect to mechanical passive movement of the foot, which also would provide an afferent volley. And these are stimulus response curves for the case of electrical stimulation and for the case of the foot orthosis. And you can see in one representative results, the statistical results are consistent, that we obtain also an increase in excitability with another way of inducing afferent feedback. And we also check what happens if instead of a single stimuli or instead of a robotic device, we was having a burst of stimuli. So basically functional electrical stimulation moving the foot electrically. And again, here you can see the differences between these interventions. Again, we have an increase in excitability, which is consistent across the modality of eliciting afferent feedback as long as the timing is precise. So basically, we studied in a series of studies this type of paradigm in which the intervention is a self-generated physiological signal, is a motor command. A BCI decode this motor command and provide a feedback which has a time locking, a precise time lock in terms of delay with respect to the motor command. And this paradigm, I have to say, has been extremely consistent. We have tested it in a number of experiments, and it's very, very consistent. Now, from the BCI point of view, the complexity of this paradigm is that it is necessary to detect these negative potentials in real time and in a precise way. And of course, when we have single trial EEG, as you know, this is very This is very noisy. And so now the question is if it is possible with a sufficient accuracy and with a sufficient time precision to detect this type of potentials. And without going into details, this is indeed possible with a reasonable accuracy. So the best performance out of a series of studies is around 80% of true positives, with quite a large number of false positives, but this performance is sufficient with the proper latency to indeed have a completely asynchronous BCI based on this associative plasticity mechanism. So having said that, we moved on, given this physiological background that we established, we moved on looking at the potential for this paradigm in clinical settings, specifically in stroke rehabilitation. And with respect to many other studies that other groups have proposed, we always stressed the precise timing. So we always stress the precise association between motor and sensory feedback. So in a first study in chronic stroke patients, in a series of chronic, in a sample of chronic stroke patients, we looked at exactly the same paradigm. So we have EEG, we have a slow cortical potential, we have triggering of a single stimuli at the peroneal nerve that provides afferent feedback. And we had two groups of patients. One is the intervention group, in which we used our physiological results so that we have stimulation around the peak negativity, where we expected to have an effect. And then we have the control group of stroke patients in which the stimulation was provided randomly in the intervals that are either before or after the peak negativity. And again, in stroke patients, we look at cortical excitability before and after this repeated intervention. So as you can see in this study, we make a step forward and we try to translate the neurophysiological results that we have obtained in this case in a clinical setting. And these are low cortical potentials in stroke patients over different days, just to prove that we can record this potential in stroke patients. They are quite well defined and they are consistent and reliable across days. And this is the latency in which we can detect these potentials online in stroke patients. And you can see we have quite a large variability, but still we can detect with a brain switch, with an interface, with a latency which is consistent with the critical timing that we were looking for according to the physiological investigations. And here is the result on this study in chronic stroke patients. And the main result is again that the group of patients who went through the associative BCI with the precise timing, as for the basic physiological investigation that we have done in healthy individuals, shows after the intervention an increase in cortical excitability, as shown again by the stimulus response curve. And the patients that went on the non-associative BCI, so where the stimulus is not exactly timed with the peak negativity, didn't have any effect. And this was a very nice demonstration in a patient population, again, of the importance of timing in these interventions. And here you have to consider that between these two cases, we are talking of just a few hundred of milliseconds difference. So this indicates how timing is crucial. In this study in chronic stroke patient, we also have preliminary indication that some clinical variables were also improving in the associative group. But we didn't go deep into the clinical outcome. On the contrary, we have then follow-up study that was probably more interesting for the clinical translation point of view in subacute stroke patients. So these are patients that are 1 to 3 months after stroke, approximately 3-4 months. And in these patients, we repeated the intervention and we also looked at more clinical outcome of the intervention. So again, we had two groups. One is the associative group that went to the associative BCI, and the other one is a sham group that underwent something similar to what I've shown for the chronic control group stroke patients, in which the timing is not precise with respect to the motor command. And here is an example. In this case, we had 12 sessions distributed in 4 weeks. And here you can see in one patient of the intervention group, day 1, we have stimulus response group, stimulus response curve before and after the intervention. Here you can see the shape of the MRCP. And here is the same patient, day 6, we have increasing cortical excitability, and day 12, also increasing cortical excitability before and after. When we look at the statistical results, the BCI group, so the group of subacute stroke patients who received the exact timing in the 12 sessions, had a very clear increase in cortical excitability as evaluated again with the MEP amplitude. And this was clearly different from the sham group, the group who didn't receive the associative BCI. And the difference between the two groups was clearly evident. And also 30 minutes post each intervention, we have the maintenance of elevated cortical excitability in the intervention group, BCI group, and not in the sham group. Interestingly, from the clinical translation, we're looking at the Fugel-Meyer assessment for the lower limb. For the two groups, these are subacute patients, both groups increase, but the intervention group increased significantly more. So we had a better functional recovery in this group. And the interesting aspect here is that these interventions are rather short. They are interventions, as I've shown before, that have between 20 and 50 paired events, motor and sensory feedback. So they are very short interventions done over 4 weeks. So these results also compare with some other BCI approaches has provided quite remarkable results. And we believe that the results are so good despite the fact that the sessions are rather short because of the timing. So we underline many times that the timing within a BCI intervention is fundamental in order to fully leverage on the associative mechanisms of plasticity. In this group of patients, this is interesting because we can look at them also in terms of functional connectivity. So in addition to having done this BCI intervention, we also recorded the high density EMG activity from these patients. This patient was from the lower limb. In this figure, you have it in the higher limb, but it doesn't matter, it's just representative. But the idea was to decode the spinal motor neuron activity and looking for the spinal motor neuron activity at how much the information coming from the brain going down to the spinal cord changed due to the BCI intervention. Basically, the idea was to infer in corticospinal connectivity, so to get an idea of the brain signal going down to the spinal cord by having a decoding of motor neurons. So in this same study, we have a full decoding of spinal motor neuron in all the in session 1 and the last session in the stroke patients. And if we look at the spectral components of motor neuron activity before the intervention, we see a very clear characteristic of stroke patients, which is a massive decrease in the beta oscillation at the spinal motor neuron level with respect to control subjects. And this decrease is due to an impairment in the corticospinal tract. And now, interestingly, after the intervention, we see a recovery with respect to the baseline before the intervention of these neural connectivity. So we are able now to look at this mechanism of plasticity through BCI, also at multiple levels, including functionally investigating what it actually, the functional implication of cortical excitability, meaning what happens when the motor signals are going down to the spinal cord and eventually to the spinal motor neurons, which tells us what could be the functional effect of a BCI intervention. So I've arrived to the end of this talk by a quick summary. I have presented to you at the beginning a classification of BCI approaches in view of the plasticity that they induce. And this is a taxonomy we proposed recently that I wanted to share with you. As I said, it's not the ultimate taxonomy, and certainly different approaches may come in between the discrete classes that we define, but it's useful for somehow putting the research in this area within a clear schematic mechanicistic classification. I've then discussed associativity as a key principle in the use of BCI or in the design of BCI for inducing plasticity. And after that, this was a bit of a broad introduction. Then I went into discussing a bit more specifically a series of studies that we have done in the past 10 years in a multi-centric approach, where we timed the peripheral stimulation, so peripheral nerves, specifically with movement-related cortical potentials online identified from EEG recording. So this would be a classical conditioning that leverage on the concepts of associative plasticity. And I hope I have convinced you that indeed the associative part is a key aspect of this paradigm. And then I presented to you towards the end our efforts in translating these concepts into a therapeutic BCI approach for stroke rehabilitation. So with this, I think well on time, Ning, I would like to thank you all for the attention. Thank you very much.
Thank you, Dario. Yes, very interesting. I mean, I know some of the, I will say most of the part, but I also see some new things that is coming. Fantastic. Okay, I think we have some questions from the audience. So the first question that I see here is from Cedric. How does the increase in cortical excitability 30 minutes post relates to long-term plasticity? Do we know how long after the stimulation session is the peak cortical excitability?
Yeah, so that's a very good question. We have so far in most of the previous studies monitored the excitability usually immediately after and up to 30 minutes after. This goes on LTP, long-term potentiation, which is a potentiation lasting at least 30 minutes after the intervention. That's why we limited to 30 minutes. We have not done a monitoring of the excitability over several minutes up to 30 minutes. So we don't know the time development, and we don't know much of the development of excitability after a time window of 30 minutes, unfortunately. But definitely it would be an interesting study to do in detail, looking at the trajectory in which cortical excitability changes over time, and probably also for longer time period.
So Dario, even in the subacute stroke study, right? So the sessions lasted, the entire therapy lasts for, I think, a month. Is that correct?
Yeah, 4 weeks.
So do we see a clear difference pre and post that 1 month period?
So in that case, we have looked always at pre and post each session, and these are 12 sessions, 3 per week. It's difficult to compare at the beginning and at the end of the month because As you know, the MEP is based on the same exact level of stimulation, but the level of stimulation has to be determined on a session-by-session basis because it changes dramatically on the hotspot position. And I mean, as you know, we have a huge variability. So to compare an MEP within a month time is very difficult. So we don't know in absolute terms what happened at the excitability within that. We know that every session had an increase in excitability. And the main result is that we know that we had an improvement in some of the clinical scores. That of course was the main outcome.
Yeah. So another question regarding MRCP, I guess, versus sensory motor rhythms. So is there any connection between these two different EEG paradigms? And do you think MRCP is a more effective paradigm compared to ERD, ERS-based methods in terms of inducing plasticity?
Yeah, so they are all waves from the EEG, and they are in different bandwidths. So the MRCP is a very small bandwidth, is almost DC. It's DC up to half of an hertz. Indeed, as you have seen some of those traces, we have deflections that last a second, 2 seconds even. So we are in the fraction of the hertz. It's a very low frequency component. Higher frequency components are associated to sensory motor rhythms, and of course we can detect by looking at higher frequency components at phenomena like ERD, ERS, and we can also look at ERD, ERS, so event-related synchronization, desynchronization together with the MRCP. Now, we started using MRCP, as I said, more than 10 years ago because we wanted to have a precise timing. So that was the main reason. So with MRCP, we have the exact time instant in which we expect the motor command going down if that was a movement executed, and similarly in case of imaginary movement. And the peak negativity is a very clear time instant. So we could do these studies with precise timing with the MRCP. We could have not done that with ERD, ERS. And we believe that having this precise association in this type of applications is really critical. So we believe that the reason why we see quite large clinical effects with relatively short sessions is because we have the possibility of being so precise with the timing.
Okay, great. I think we have a last question, since you have a very short, maybe a quick answer about the decomposition. I think that that you showed in the last regarding the recruitment patterns or the coherence of the stroke patients. So that can only be done by high density EMG analysis. Is that right?
Well, it is also possible by intramuscular EMG. So one can assess spinal motor neurons by placing electrodes or on the skin. When it is done with surface EMG non-invasively, it is particularly reliable when you have an high density system. So the larger is the number of electrodes, the more reliable is that decomposition. So in a non-invasive approach, a large number of channels is needed for that type of analysis.
So this is actually a question from myself. So the coherence plot that you show is that between two EMG signals, like interference patterns, or this is between two motor unit trains, or between two populations of motor units?
Yes, thank you, Ning. This is I went very quickly because in the interest of time, since we are slightly late, I wanted to be a bit short, but this required a bit more time, and your question is excellent in this respect. So what we do for looking at coherence plots is that we take, so this is, for example, a population of 25 motor neurons decoded from a stroke patient. We divide this population in 2 random groups, and we make a permutation of these groups. And then we make the coherence between the cumulative spike train of one group with respect to the other. Then we make permutations with a number of groups, and we make the average of all the coherence plots. So what does this give us? This gives us an indication of the common synaptic input that those motor neurons receive. So it gives us an indication of the spectral bandwidths where the motor neurons receive a common input to the full population. And different frequency bands tells us different functional relevance of that input. So for example, the beta bandwidth tells us the input to those motor neurons.
Great. Okay, thank you. There are a number of other questions that I will forward to you on the Q&A area, Dario, for you to maybe to follow up. And now I will give the moderator role to you, Dario, to introduce our next speaker. Okay, I cannot.
Yes, Inga, sorry, I muted that. Yeah.
Okay.
So, next speaker, and I believe last speaker also of the day and of the workshop is Amy Osborne, and she will talk about adaptive decoding algorithms. Please.
All right. Thank you so much to the organizers for this great workshop and for the invitation. Just a quick double check that you're seeing slides okay?
So we can see them perfectly. Thank you.
Yeah, great. All right. Great. So my lab works on motor BCIs, which we've heard about quite a bit during this workshop. And when we think about a motor BCI, our mind often immediately goes to the decoding algorithm. If we understood exactly the encoding of movement in the brain, we could build just the right decoding algorithm to extract the control signal that we would want to send to an exoskeleton or a motor prosthesis. But this is just a small piece of what's actually happening when a user is controlling a BCI. So that control signal goes to the device that then moves, and they have sensory feedback in real time. And so the brain is in a closed loop constant dialogue with the device itself. And decades of research have really highlighted that this feedback induces plasticity and learning, like we heard about earlier today. And so this changes sort of the nature of the problem of what we're doing in a BCI, and we're not just trying to decode natural movements. And I tend to think about it as actually trying to build a new motor system that the brain has to learn how to control. And so this is a harder problem, but it also opens up really exciting opportunities. So we can now start to think about how we can leverage learning in the brain to actually improve BCI performance. And then also opens up opportunities for thinking about how to use BCI for rehabilitation applications, as we've seen throughout this workshop. And so I'm interested in kind of thinking about these new opportunities that are opened to engineer learning through BCI technologies. And our group, in kind of broad strokes, approaches this in two different ways. So we first are interested in kind of re-engineering the BCI problem to try to optimize learning in the brain. So we can treat the brain as some kind of black box. We know it's learning and adapting in some way. And then we can think about how we can control the other elements of the engineered system, for instance, the decoding algorithm, to try to make the brain learn in an optimal way. But then we're also really interested in sort of the actual neurophysiological mechanisms of learning that are happening in a BCI. And so here the goal would be to actually open up that black box and understand more about how the brain learns. And the goal here would then be that these two threads of research are ultimately going to inform each other. So as we understand more about the details of how the brain is learning and changing, we can improve our therapies to leverage that learning. But also where our devices might be failing, we could point to questions about how the brain is learning and changing. And we do all of this work in a preclinical animal model of motor BCIs. So we work with rhesus macaque monkeys, and we train them to do basic motor behaviors. And then we do invasive implants into motor areas, typically motor cortex, primary motor cortex, and premotor cortex, to record activity of neurons. And then we use that neural activity as input to a decoding algorithm. And here, because we're interested in understanding kind of the detailed mechanisms of how the system works, we kind of keep these decoders typically very simple. So linear filters, like for instance, a Kalman filter, will just map the firing rate of neural activity into the kinematics of movement. And the movements that are being controlled, again, we keep relatively simple. So virtual movements, like controlling a cursor on a computer screen. So the position and velocity in continuous time. And the animals then have visual feedback of that cursor movement, which creates that closed loop control system. And so in a BCI, like I mentioned, there's brain plasticity has a lot of potential benefits. And so one in particular is that users over time can gain sort of a skill of controlling a BCI. So much like how you would master the sport of tennis, skill allows you to retain that performance over days. So when you come back the next day, after a practice session, you're just as good as you were the previous day, and you can continue to build on that performance over time. That skill can also be resistant to interference. So for instance, you can learn to play tennis and badminton as well and switch back and forth between those two. Similarly, with skill learning, users can actually control multiple different kinds of BCIs and shift back and forth. So these are really potentially very useful properties of a BCI, but some of the problems with relying just on brain plasticity is that these processes of forming those skills can be relatively slow. It can take weeks to months for people to master these devices. And importantly, it requires stable neural recordings. So if, for instance, we're recording from 100 neurons, from an electrode array to control the movements of the cursor, and there's shifts in neural recordings, like we've heard about from Juan Gallego, that disrupts the brain's ability to actually continue to learn that skill over time. And also, it seems some interesting evidence suggests that not all decoders and BCIs are kind of equally learnable. So it's not obvious how to design a BCI ahead of time to make sure that the brain can reliably learn this skill. But fortunately, the brain is not the only learner that we have in a brain-computer interface. So we also have machine learning technologies that we can use adaptive decoding to try to adapt the decoder to the brain. And so there's been a lot of really great work, including my work, trying to develop algorithms that can do this adaptive decoding to improve performance. And importantly, adaptive decoding kind of has a pros and cons list that looks almost like the mirror image of brain plasticity. So I've been able to develop, for instance, algorithms that improve performance very, very quickly on the timescale of minutes. And these algorithms are really robust, so you can initialize decoder parameters completely randomly and very quickly train up a decoder. And you can use adaptive decoding to track neural recording changes over time and still maintain high performance. But a lot of work shows that if you just rely on machine learning alone and are constantly regularly changing the decoder algorithm, you kind of create a moving target for the brain, and that might limit the brain's ability to actually master that skill of controlling the BCI. And so with these two different learners, there's a lot of interest in potentially, with sort of mirror image pros and cons, it opens up this possibility of, can we actually leverage both with co-adaptation to actually have the brain and a decoder algorithm adapt and learn together in a synergistic way. And so in my PhD with Jose Carmina, we did a study to demonstrate that this was in fact potentially possible. So we had an animal, and we used adaptive decoding to initialize the decoder parameters. So what I'm showing you here is performance, percent correct on a simple cursor control task across different days. And on the first day, we start with completely random initial parameters of a decoder. We then use an adaptive decoding algorithm called smooth batch that, in the interest of time, I won't talk about in detail, but I encourage you to look up the papers if you're interested. So we use that adaptive algorithm to boost up performance. And this example that I'm showing you, we sort of purposefully didn't adapt to full good performance because we wanted to see if the brain could continue to learn from there. And then we keep the decoder fixed whenever possible. But if we have a change in neural activity due to recording instabilities, we can use adaptive decoding to make sort of small gradual changes over time. And that's what is shown by these other blue dots. And what we found is that by doing this process, we were actually able to kind of get the best of both worlds, that we have very stable performance and learning on the part of the user, suggesting skill, while still even in the presence of these sort of gradual changes in the decoder to deal with recording instabilities. And when we then looked at what was happening in the brain, what we found is that as performance stabilized, the neurons are developing sort of a stable encoding representation of how they're controlling this task. And so here I'm showing you, for instance, just the direction tuning of a neuron. So the direction the cursor is moving and the firing rate on the y-axis there. And over days, you can see that this neuron consistently prefers the same target, but is gradually increasing its modulation for the task. And I won't go over details, but this we also found that there's sort of a really interesting relationship between the encoding changes we saw in the brain and the decoder adaptation that we were doing. And it suggested that there were, in fact, these synergistic interactions between these two learners that we could potentially leverage. So this is very exciting, but I'll be the first to acknowledge that that study sort of just picked one strategy for co-adaptation. And we by no means know what the actual optimal approach for doing that is to optimize performance in the system. And so this is kind of a really interesting question to start thinking about. And so let's take a step back first and think about what exactly is being learned by the brain and the decoder in a co-adaptive system. So in a BCI in general, we're mapping neural activity to cursor positions, but there's actually a lot of transformations that are happening in between. So we have a brain, and we're putting electrodes in somewhere in one of the many possible motor areas, like primary motor cortex. We then have electrodes that, of the millions of neurons in motor cortex, are picking up the activity of just a small subset, so the purple ones that I've highlighted there. And then the activity of those neurons are mapped through the decoder to control the cursor movement. And so in all of these different transformations, it's interesting to think about the fact that there's at least two different kind of learning problems that ultimately have to be solved. And so I think about it as first a sort of modulation learning problem or a credit assignment problem, where the brain has to figure out which of the neurons in the brain are actually being mapped to the cursor. If they do not generate reliable patterns of neural activity in those purple neurons, the cursor would never move. And then there's the second problem of the mapping. So given a pattern of neural activity in those neurons, how does it relate to the cursor movement itself? And so adaptive decoding is really helpful for kind of simplifying that mapping learning problem. Given a pattern of neural activity that the user has generated, we can try to update the decoder to smartly map it to a given cursor intention of movement. And with co-adaptation, what I would argue we've done is that we've figured out a way to adapt that decoder and not get in the way of the brain solving this modulation learning problem, but we're also kind of not really controlling it or promoting it in any way. And this I see as potentially a concern because at the end of the day, that pattern of neural activity, the brain's encoding, that modulation learning problem is the real bottleneck of final performance. if the user can never figure out how to generate a useful encoding in that pattern of neural activity that we're using to control the cursor, it doesn't matter what kind of adaptive decoding I do on the other end. And so that might seem like potentially a kind of theoretical problem and concern, but some recent, one of my grad students, Pavi, has been looking at the neural activity patterns in that co-adaptation data set that I showed you to actually show that there might actually be some learning phenomena that happen in the brain that could be optimal for the brain, but are not necessarily globally optimal for the BCI system and are potentially problematic for us as engineers. So what she is doing is looking at the patterns of neural activity across all of the neurons that we're recording and building a classifier to try to look at how those patterns of neural activity relate to the targets that the user is trying to get to. So just to be clear, this decoder that we're building is separate from the decoder that's being used to actually control the BCI itself. And in this analysis that she's doing, she's looking at both what we call readout neurons, so a small subset that are actually being mapped through the BCI decoder to control the cursor, and the non-readout neurons. So these are other neurons that are nearby, but are not actually directly controlling the cursor. And so now what we can do is look at, once we train these classifiers, we can look at the coefficient matrices to try to understand which neurons are contributing to the task control and how. And so this is one example of this coefficient matrix, and time is on the x-axis, and then neurons are on the y. And we've arranged the neurons so that the readout neurons are on the top, and then the non-readout neurons are on the bottom there. So if we compare this coefficient matrix in an early session to the coefficient matrix in a late session, we can see that there's very clear changes in the representation. And there's kind of two key things I want to point out to you. First is that the non-readout neurons kind of quickly start to deactivate. So they no longer are really generating reliable firing patterns of activity. And this has been observed previously and suggests the brain does seem to solve this kind of credit assignment problem of figuring out which neurons are mapped to the BCI. But then if we look at the readout neurons, we see that the brain actually seems to learn an incredibly sort of sparse representation where there's really kind of just a small number of neurons that are contributing to the movement. And so there's just a really small subset of neurons, which is really interesting to understand why the brain might be doing this. It might be all the brain needs for these very simple cursor control tasks. But from an engineering perspective, this starts to become problematic because if you think about it, now we have a BCI where if that neuron, that one or two neurons that are primarily controlling movements to this direction are lost, it doesn't matter how much I adapt the decoder, the encoder no longer has of the brain, doesn't really have a clear representation that I can use. And so the BCI now becomes very fragile. So this creates this sort of is one example of where the encoding in the brain and these learning dynamics could potentially create challenges for us. More broadly, we've heard reference to these phenomena like BCI inefficiency, where users in general sometimes seem to actually struggle potentially to solve this modulation learning problem at all. And so we're really interested in this idea of whether co-adaptation could be used to actively shape the user's encoding in some way. And so this might be useful to actually make the brain's representation optimal for the decoder that we're using for BCI control. And you could also think about this potentially being useful for rehabilitation applications as well, like we've heard about in the workshop. And so this is a big ask, and I won't propose that we've actually solved this problem yet, but towards this goal, we're now starting to think about kind of new computational approaches for co-adaptive BCIs so that we could start to think about solving this problem. And so that's what I want to talk to you about in the last few minutes here. So my grad student, Manishka Maduri, has been working along with a collaborator, Sam Burden, who's a control theorist, to start thinking about new ways of approaching the co-adaptation problem in BCI and shifting from a sort of purely machine learning perspective towards one of control theory and game theory. And so we built a really simple model of how the brain and the decoder might be adapting. And so we're just simply modeling the brain as a linear relationship between firing rate of neurons and target position. And then the decoder is sort of a mirror image that is trying to relate firing rates back to user intended positions. But importantly, we model how the brain and the decoder adapt by giving each one a cost function that's not necessarily the same. And so we say that the brain cares both about optimizing the performance of the task, so that's this error term here, but it also cares about you could think of this as an effort term. It basically says, I want to change, but I want to change as little as possible to optimize performance. And the decoder is similarly trying to conserve its movement over time. And so in doing this, it allows us to now think about co-adaptation as the brain and the decoder playing a game with each other. And this particular formation of our cost functions has a really useful form where it creates what we call a potential game. That's useful in game theory because it's very analytically tractable and potentially very useful. Because we can write down one thing called a potential function that describes the dynamics of kind of the whole system. And so by doing this, what we can now start to do is think about for a given brain encoder and brain decoder and different adaptation rates, how is this system going to evolve? So for instance, we can try to predict the equilibrium points of how this system is going to settle, which is pictured here. And so for instance, we can demonstrate that the equilibrium of this system is going to depend on these effort penalty terms, which is sort of intuitive given that if the brain, for instance, doesn't want to move very much, that will influence where the final solution resolves. And also, of course, the learning rates are going to influence things. And for example, our model recreates some important observations from both prior models of co-adaptation as well as experiments that you can actually create very unstable systems if you don't have a decoder that adapts faster than the user. And so I'll try to wrap up quickly here, but the main thing that I'm excited about or interested in is this reframing of co-adaptation as a brain now allows us to start thinking about decoders that don't just assume that the brain is right and try to only optimize task performance, but instead start to think about shaping the user's learning and encoding actually as an objective of the decoder. And so to conclude, the brain's encoding potentially could be a bottleneck for motor BCIs. And so we're really interested in thinking about how we can leverage learning within the brain to actually sort of shape that encoding, which could potentially be useful both for optimizing performance and for rehabilitation. And so we're now proposing this kind of new game theory way of thinking about co-adaptation in BCIs that we're excited to test in experiments to see how this plays out. And so with that, thank you to the organizers and everyone in the audience for your attention, and of course to my lab that is doing all this work.
Thank you very much, Amy, for a great talk and also perfectly on time. That's fantastic. So I'm not sure, Ning, that I have understood how to look for the questions on the chat, but I may start with one, and then maybe Ning, you can you can provide the question, or you can ask the question from the audience. It was quite interesting as you underlined this sparse representation of the task in terms of the motor neurons involved. Indeed, it's very interesting. As you say, maybe that the brain does need a very small amount of neurons to do this very, very simple task with respect to the complex task that normally it does. But my question is that sparse representation specific for the cursor reaching task that you have designed, or is it a more general characteristic of this type of tasks?
Yeah, it's a great question. So we have some other data, for instance, from this animal doing other BCI control tasks, for instance, where so these were just point-to-point movements that are very, very simple, but we also asked them to navigate around obstacles. And then we also had them do a couple tasks where, for instance, they had to do one thing with their arm while then also controlling the BCI. And so that's going to be a really interesting direction to look at whether those sparse representations persist even across those different kinds of tasks. We're also actually put it here on the slide, but that project is part of a collaboration with Guillaume Lajoie, who builds a lot of really useful artificial neural network models. And we're trying to understand, where does this sort of very simple representation come from? Is it related to the task, or is it some kind of more, is there some sort of neurophysiological basis for it?
All right. And then as a follow-up also, just to confirm that I well understood, the game theory approach that you have described at the end, is one of the aim of that approach to reduce the sparseness of the representation specifically? So is the main aim to increase the number of neurons that would encode the task?
Yeah, that would be one potential application. So the idea would be that, the brain left to its own devices might try to learn a very sparse representation, but that you could, if you had a decoder that was trying to optimize the encoder, you could sort of force the brain into a different part of the solution space that was no longer quite so sparse, which is a different way of basically, can we make it easier? Can we force the brain to do something that's a little bit easier for us to decode on the other end, right?
Yeah, no, thank you. Very, very interesting. Thank you. Even I'm not sure I can see the question. Maybe I will.
Oh, I can directly ask. This is actually a very nice talk. I have been following your own work for a very long time. I want to ask two questions. The first question is that I noticed the sparse representation in a BC control, the BC part. But I noticed that this readout, like neurons, is identified by the classifier. So I'm assuming that this is classifier using like the labels of the movement. So that assumes that the monkey has completed the task or well-trained with this task. So I'm wondering if this is not a well-trained case, but a learning case. For example, the monkey is explore how to do this brain task, not like I'm already well-trained with the brain task, so I'm totally fine with the brain task. Do you think the representation will be still like the readout neural representation would be still sparse?
Right, yeah. So our sense, and this is, consistent with other nice work from coming out of the Carmina lab and a few other groups, like Steve Chase. My sense is that the part of the learning process is kind of forming this sparse representation. So it doesn't, I don't think the brain, I think early on, there's a lot of variability in the neural representations that then sort of coalesces. So as, through probably sort of operant conditioning mechanisms and other neural plasticity mechanisms, sort of the brain is eventually making the association, right, that, oh, when that neuron you know, has this firing rate, I managed to hit this target, right? But that representation doesn't exist initially, and so but through that sort of reinforcement mechanism.
So you were saying that. So you were saying that the representation kind of converged to this sparse version. So yes. Then the following question would be, if during the learning, like during adaptation to learn the spring control, then we're not assuming that we can correctly label the action for identifying the readouts like neurons. In this case, how could we see their representation in space?
Right. Yeah, that's okay. I think I understand the question. It's a good one. It's a hard problem, and I don't have a satisfying answer for you yet, but I think that there's been some really interesting studies that definitely suggest one approach that people have used, for instance, is that you can if you assume, for instance, that like the direction tuning of a neuron is not going to change between like arm movement and BCI control, you can then use that information to decode, you know, what the user's intended direction would be in BCI. And there have been arguments that using those approaches that sort of suggest that that the subjects are performing like a re-aiming strategy early on, where if I want the cursor to go up, I have to think about going right. And so you can, that is sort of the most common other approach that people have used, but it requires assuming that the encoding isn't changing at all, which of the tuning, and I'm not positive that that's necessarily the case. And certainly, particularly in longer time scales, it seems like there are plasticity mechanisms that then change the sort of tuning representations of the neurons. And so it's a difficult ball of wax to kind of fully untangle.
Yeah, I think that actually makes the identification of the neuron that actively involved in this learning procedure very important.
Yeah.
Yeah. So that last question, very short one, is that because you mentioned about this optimal control between the brain and the decoder, and you define the causal function for the brain. And I wonder why you use the second norm for the weights, because you just mentioned that you think there is a sparse distribution to support this brain control. So generally, I'm not sure why you use a second norm instead of a first norm.
Yeah, that's actually a very good question. So that work, yeah, I will completely admit that we sort of, to some extent, those cost functions, particularly for the brain, were chosen for mathematical tractability purposes, for kind of understanding system dynamics. I won't propose that these are necessarily exactly what the brain is doing, and I think that will be, so our next steps with that project are to actually start building interfaces and testing, you know, how well the model actually predicts, and also using existing experimental data to see whether, for instance, we have to change our models of the brain cost function. So it's a really interesting direction, because one of the reasons that, you know, trying to think about optimizing co-adaptation is so difficult is that we have so many unknowns in the system, right? We don't know the brain's cost function, but the hope is that we can, with some experimental data, at least make some inferences about the general shape of it. But I think that's part of where pairing this with basic neurophysiological studies to try to dig into what the brain's learning mechanisms are will be really important.
Thank you very much for your presentation.
Actually, a question from, I think it's an important question from Professor Helen Huang for Amy. So it goes like, thank you very much for the very great talk, Amy. Could you discuss more about how to handle learning rate differences between brain and machine? And also, if the goals are different between human and machine, how to formulate the problem based on a game theory?
Yeah, so with the learning rates, the main observations that I've seen both experimentally and that fall out of the model are that most cases it's always better for the decoder to adapt much faster than the user. But in general, that you don't want to, but that doesn't mean necessarily to always adapt as rapidly as possible, because you also want to avoid, if your decoder parameters are not converging in some useful way, then you want to avoid adding lots of noise that then the user has to track. And so the goal would be to have a decoder that learns very quickly, but that also converges to sort of stable solutions. And then on the question of different objectives, so that's actually part of the decoder and the user having different objectives is what makes game theory kind of a useful theoretical framing for thinking about the problem. The example model that I showed kind of for kind of mathematical tractability reasons makes the two kind of mirror images of each other, but that isn't necessarily required. So you could have a decoder that has, you know, many additional terms, and similarly a user that has different terms. It just no longer becomes, for instance, a potential game that is nice and tractable and has sort of a lot of useful theory framing around it. But as a general rule, they could have different cost functions. So I hope that is a useful answer.
Okay, thank you, Amy. I think that's a very nice answer to the question. Okay, so thank you very much, Amy. I think Dario would like to share his screen.
Yeah, Ning, I think we go to the conclusion of the workshop. Now I can share. Sorry, yeah. Yeah, so yeah, thank you again, Amy. Indeed, and this closes the session. It also closes the workshop, and so Ning, Even, and I wanted to just say a few words to close the workshop. So, well, oops, yeah. Well, first, my name is first in the organizers, but Ning and Even actually did all the work and put a huge amount of effort. So thank you, both of you. Here is just to remind you all the sponsors we had, and just a few screenshots that Ning has collected and show all the people who have been intervened and giving talks. We had 22 speakers, as you know, divided in 4 days. So this has been a great, really great program. So thank you to all the speakers and the attendees. Here is some other shots of speakers and discussions and talks for you to remind the past 4 days. As you can see, and also the variety of topics that we've been discussing. So there have been 96 participants. This is the division, just for those of you who like a bit of statistics and checking where participants came from, and also in terms of division between more junior and more senior researchers. However, in this type of meetings, as you know, the number of participants is not as important as the number of people that actually view in streaming the talks. So the numbers here are impressive. So we have viewer numbers almost 5,000, and in particular the first day, I believe, it was extremely high in terms of number of viewers. So very, very big success. Certainly thank to an impressive program and the efforts of all the panelists in giving a very broad overview in the field of neuroengineering and rehabilitation. So this has been great. Ning is under, well, as agreed on with the Frontiers in Neuroscience and the IEEE Transaction in Neurosystem and Rehabilitation Engineering for special issues that can be dedicated to the workshop, opening also to the attendees and to any other who wants to contribute. More information will come. This is a very nice initiative also to have a publication to support as a sort of a proceedings of the workshop to come. And then to close, we should discuss where to meet next time and how to continue this important initiative. And I think I will leave the discussion on this to Ning, and also I will leave the final word to Ning, since he deserves to properly close the workshop. Ning.
Thank you, Dario. As many of you know, that this is the second iteration of this neuroengineering and rehabilitation international workshop. As Ivan is here, so Ivan organized, and I think with Professor Principe, and organized the first workshop I always say last year, but the year before, because 2020 is indeed a black hole in my mind. It was a very good workshop and a very big success. That's why we thought, yeah, we should have another workshop like this. Hence, that's the reason we're here. I think this is also the last 4 days in a virtual format. I think we also have a very successful workshop in terms of the viewership, in terms of the questions we have, in terms of the speakers, the breadth and the depth of the talks that we have seen here in the last 4 days. So it would be natural for us to think about what do we do next. So I will be also, of course, communicating with the participants, with the panelists about when, where, and how. Hopefully, the how will be resolved soon with the COVID, with the vaccine efforts around the world. So maybe we can meet sometime next year in a face-to-face format. But I will look for suggestions from the panelists, from the audience, that on the when and where. And with that, I would like to again thank you very much for every participant, and particularly for the speakers that take your time in the last 4 days to give us fantastic talks that is inspiring and very very informative on where the general area of neurorehabilitation and engineering should go. So with that, I'm handing over to Ivan. Professor Wang, do you have anything like you think that? Hello, Ivan.
I don't have anything further. I just want to thank all the speakers for their presentation and all the participants who asked great questions. And hopefully we can see each other soon, somewhere, face to face.
Okay. Well, and yes, so before we're closing the workshop, I'd like to also thank the student volunteers behind the scenes that you don't see, in particularly in a virtual session. In the physical session, you see the students running around with t-shirts and everything. But now with the virtual session, you don't really see them at all. But they have done a lot of work behind the scenes to make the things happen. Yes, so thank you. And as I said, hopefully we can see each other sometime soon in a face-to-face fashion. With that, I would like to close the entire workshop. And thank you, everyone. Thank you. Bye.
Bye.
Thank you. Bye.
Bye-bye.